Hello students, so this is the second class number 2 on the topic work, energy and power. In our last class we were discussing about the meaning of work, when the work is positive, when the work is negative and when the work will be negative. Okay, and we are discussing the SI units, right? So later we discuss how to get the work in case of a variable force as well as the constant force. If it is a constant force, we can apply the formula W equal to force into displacement into the cos theta. If it is a variable force, so you have to draw a graph. You have to draw a graph of force versus the displacement. And if you get the area under the curve, so first you should take a small segment and get its area, and if you increase it, okay, if you get the area of small segments of small segments in that curve, so you will get the total area under the curve, that will be the work done. Okay, and also discuss about the energy. What by energy? So energy is the capacity of doing the work, and there are in your PUC first year we mainly focus on the mechanical energy. So and we know mechanical energy is the sum of kinetic energy and potential energy. Mechanical energy is the sum of kinetic energy and potential energy. So the SI unit of energy is joule. SI unit of energy is joule. Energy is joule, and we use the one more unit. Which is called electron volt. So if you want to measure a very small energy, and today we will discuss the work energy theorem. You may get a 3 marks question, state and prove work energy theorem. So the statement is, and we know the relation between work and energy. How much work will done, that much of energy made there. How much energy is there, that much of work will be done. Okay, so work energy theorem. So as per this one, the change in kinetic energy of a body, is its work done. Is equal to work done. The change in kinetic energy of a body is equal to work done. Okay, so it's not only for the kinetic energy, we can also write it for the potential energy. First we will say about the kinetic, later we can go for the potential. So statement is the change in kinetic energy of a body is equal to the work done. Okay, so I can prove it by taking an example. So there is a body, so it's a surface now, and we are assuming it is a very smooth surface without any friction. Okay, this is the body of mass m. So initially it was under the motion u, it was under the velocity u. Okay, so it's moving with the velocity u. Okay, somehow we applied a force here. We applied a force on the body in the same direction as that of the motion. So as a result of the force, there is an acceleration. As a result, the velocity of that body changed to v. The velocity of a body is changed to v. Okay, so we should write, consider a body of mass m moving with initial speed u. Okay, as a result of applied force, its speed or its velocity. Okay, I'll write velocity. Its velocity is changed to v. Its velocity is changed to v by covering a distance x. Okay, so by traveling a distance x. Okay, so the explanation, and as per the kinetic equation, v square equal to u square plus 2ax. Okay, I can write it as v square minus u square equal to 2a into x. V square minus u square equal to 2 into a into x, and then multiply by 1 by 2m, multiply by 1 by 2m on both the side, on both side, multiply by 1 by 2 on both side. So here if I multiply 1 by 2 m, 1 by 2 m v square minus 1 by 2 m u square, like this. So here this become 1 by 2 m v square minus 1 by 2 m u square equal to, here 1 by 2 and this 1 by 2 cancels, 1 by 2, or I can write one more step. Here this is 1 by 2 m and the remaining term there 2ax. Now 2 cancel, is it? So this is 1 by 2 m v square. V is the final velocity. So I can say it is a final kinetic energy. This is final kinetic energy. So substitute F indicating final minus 1 by 2 m u square. U is the initial velocity. So that's why this become initial kinetic energy is equal to, here it is remaining term m into a into x, right? And was a ma, why applied that much of force? So here this is kf minus ki is equal to f into x, f into x. So force into displacement. So for the force into displacement we write it as the work done. This will be the work done. So you can say change in kinetic energy, change in kinetic energy is equal to the work done, is equal to work done. So this may ask you for 3 marks. This may ask you for 3 marks. You can note down this one. Is it? Okay. So similarly, we can also prove the same concept by taking the potential energy, by taking its potential energy. We can write the change in potential energy. The change in potential energy of a body is equal to the work done. Initially it was, okay, in previous case I have taken the kinetic energy. You can prove by taking potential energy also. So 3 marks ಕೇಳಿದ್ರೆ ಅದೇ ಬರೆಯೋದು ಬೆಟರು. ಇದು ಇರಲೇ ನಿಮ್ಗೆ ಹಂಗೆ ನಾಲೆಜ್ ಇಲ್ಲ ಅಂತ ಹೇಳ್ತೀನಿ ರೀ ಇವಾಗ. So this is the ground now. There is a body here at a height h1, at a height h1. Oh, and we have lifted it up. We have lifted it up for a height h2. And the distance between these two is, I call this is d. Okay, initially the body is at height h1. Okay, later it is lifted to the height h2, and the displacement of a body is d. Okay, I can write the initial potential energy. Initial potential energy as mg h1, and I can write the final potential energy as mg h2. Is it? So final minus initial, Pf minus Pi is equal to mg h2 minus mg h1. So you can write it as mg into h2 minus h1. So m into g is nothing but that gravitational force. Okay, this is F, and h2 minus h1, h2 minus h1, this is nothing but the displacement. Force into displacement, again it will give you the work done. Work done. So what is equal to Pf minus Pi. So here it is a change in potential energy of a body is equal to work done. So you can prove it in both the kinetic energy case or potential energy case. Next one, conservative forces and non-conservative forces. What is a conservative force? If the work done by a force is independent of path, and depending on initial and final, positions only, then the force is called conservative force. It is called a conservative force. Okay, what it mean? Say for example, there is a work done by particular force and it is independent of the path followed. What by independent of path followed? What by depending on initial final positions only? Okay, say this example. So this is the ground now. The body is initially at height h1. Okay, finally it reached the height h2. Okay, it reached the height h2. So work done, if I say to calculate the work done, you say first this is the Pi and this is the Pf. Is it? So you take a Pf minus Pi. This portion. See if you lift that body in this way, so the work done, for example, here to here, I say this is 10 joule. Okay, if you lifted that body like this, so ಇಲ್ಲಿಂದ ಇಲ್ಲಿಗೆ ತಂದೀವಿ ಬಾಡಿ ಟ್ರೀ 10 joule ವರ್ಕ್ ಆಗ್ತದೆ. Suppose you have carried that body in this direction and you kept it here or you kept it here. Okay, first case, second case and third case. So in all these three cases the path followed is different. First you have carried it normally, later you have like this and you have like this. So in all these three cases, if I say what's the work done, so you take the potential, initial potential energy and you take the final potential energy in this case. Okay, so if this is a 10 joule, there also 10 joule, there also 10 joule, is it? So this is called that work is depending on initial point and final points only, not on the path followed. Suppose you have taken the body like this and finally you keep it here, or you can take like this and finally you keep it here. So somehow the height is same in all the cases, the distance is same in all the cases, and the force is same for all the bodies, sorry, or in all the cases for that body. So that's why I say it is independent of, path followed. Say independent of path followed. On what factor it depends? It depends only on initial position and final position of the body. Okay, so example for this one, example for the conservative forces. Okay, this force, so on which force, sorry, by which force the work is acting here? That force is the gravitational force. So gravitational force is a conservative one, gravitational force is an example for a conservative force, because due to this force, due to this work, the work done is depending only on final and initial position, not on the path followed. Okay, and also electromagnetic force. Okay, so these two are the examples for the conservative forces. And next one, non-conservative force. What do you mean by non-conservative force? See here, the reverse case, if the work done by a body, is depending on path followed, by the body, okay, then the force is said to be non-conservative force. And we know if there is a work done, there must be some force. If that work done is depending on the path followed, then the reason that causing for such a path following work done, so that is called the non-conservative force. For example, all the opposing forces are called the non-conservative force. Like what are opposing forces? Like in our last topic we have discussed about the friction, which was always opposing the relative motion of the bodies. So friction is an example for non-conservative force. And also viscous force is also an example for non-conservative force. And the next point is conservation of mechanical energy. And we know the conservation word. Conservation means is a constant. Okay, so conserved, it will be constant, that quantity will be conserved or constant for all the cases, that is called conservative. Okay, and we know the conservation of energy can neither be created nor be destroyed. The total energy of a system or total energy of the universe is always constant. Okay, but here we are discussing, or we are restricted only about the mechanical energy. Is it? Okay, what it mean? Conservation of mechanical energy. So the total mechanical energy of a system, always remains constant, or you can say conserved, remains constant or conserved. And that there should be a condition to say conserved under, so that condition is under conservative forces. Okay, if the energy is associated with, if that energy is associated with the conservative forces, then we call that mechanical energy is conserved. So the mechanical energy of a system always conserved under conservative forces, under the conservative forces. Is it right? Okay. And you may get a 5 marks question. You may get a 5 marks question. State and prove. State the law of conservation of mechanical energy and prove it in case of freely falling body. Okay. So prove in case of freely falling body. So this becomes the statement. What is that? The total mechanical energy of a system always a constant or a conserved under conservative forces. Right? Okay. So then for a freely falling body, can you prove it in case of freely falling body? Yes, definitely, because the freely falling body is under the action of gravitational force only. So if it is under the gravitational force only, then we call it as freely falling body. Is it? Okay. So then conservative force, gravitational force is a conservative force, and the body is falling due to the conserved gravitational force. So that's why we can prove the mechanical energy is conserved for a freely falling body. How to prove this one? Okay. So here proof of conservation of mechanical energy, conservation of mechanical energy in case of freely falling body, in case of freely falling body. Okay. So it carry 4 marks. This is 4 plus statement 1. Finally you are having 5 marks. Is it? Okay. I take a 3 positions here. This is our ground. This is the ground. Right? There are 3 positions. This is A position, this is B position, and finally on the ground this is C. On the ground it is C. Okay. So we have to see, was a total mechanical energy in A point separately and B point separately, on the C point for the same body separately. If the total mechanical energy at the C, at the B, and sorry, at the A, at the B, at the C are same, then you say that mechanical energy is conserved if it is same in all the positions, in all the cases. Okay, let us see one by one. Case number 1. So case number 1 ಏನಂದ್ರೆ, when the body is at position A and at rest. When the body is at the position A, okay, this is our diagram, at the position A at rest, in the position A at rest. Okay. So in such a case, what is this total energy? Can we calculate its potential energy now? When the body is at h, at a height h. Sorry, when the body is at a point A at a height h, and its distance is now h. Its distance is h. Okay. So you can write its potential energy m into g into h. And what about its kinetic energy? So the body is at rest. So the initial velocity u equal to 0. It means its kinetic energy is 0. So what about the total mechanical energy? Total mechanical energy is equal to the sum of potential energy and the kinetic energy. Here the kinetic energy is 0, only term is potential energy, that become mgh. Say equation number 1. So this is equation number 1. Is it clear now? Okay, at a position A. Then I take the second case. Here. Okay, case number 2. Okay, how do you take this one? Okay, I'll show by the diagram. By the diagram. Now the body is not at A only. Okay, now the body is falling from A to B. A to B point. So by traveling a distance x. So this was the body and initial velocity is 0. And if it is under the motion, it is having some speed. This is Vb. Velocity. Initial velocity is 0, and it is moved from A to B point. Okay. So my second case is case number 2. When the body moved from or when the body is moving from, the body is moving from A to B, and the body is moving from A to B. So it is moving from A to B. This is our A position, and this is B position up to here. And how long, how much distance it has covered? X, is it? And what about the remaining distance here? If total distance is height, now this is x, and the remaining distance is h minus x. Is it right? Is h minus x? Okay. So then, what are the potential energy in this case? The body is at a position B, and it is at a height h minus x. So you can write its potential energy as a m into g, as it is. Its distance changed as a h minus x. If it was here at distance is height, now its distance, its height is h minus x, because x distance travelled. Alright, mgh. What about the kinetic energy here? Is it having kinetic energy or not? See here, we have dropped that body from a particular point and start to move, and I am observing it at a B. So now that its motion is stopped, it has to fall on the ground to stop its motion. So now it is at a point B and observing when it is at B only. It is having some speed, so that is Vb. So that's why its kinetic energy is 1 by 2 m into Vb square. 1 by 2 Vb square. How to get the Vb value now? How to get the Vb value? So this is final velocity, this is initial velocity, and traveling distance is x. So you can write Vb square, speed at the B, or velocity at B square, is equal to initial velocity plus 2 into A value. Acceleration, ಯಾವುದು acceleration act ಆಗ್ಲಾತದೆ ಇಲ್ಲಿ? The acceleration is acceleration due to gravity, and the distance traveled is x. So Vb square is equal to 0, initial velocity is 0, and 2 into g into x. So we can write Vb square equal to 2gx. So kinetic energy is equal to 1 by 2 m, as it is. Vb square in berili nana, instead of writing Vb square I can write 2 into g into x. Now this 2 cancel, so the kinetic energy is equal to m into g into x. It is m into g into x, right? And this become your kinetic energy, and this become your potential energy at the point of B. Okay, so therefore total mechanical energy is equal to the potential energy mg of h minus x, it is here, plus the kinetic energy mgx, is it? And simplify, this become mg into h minus sign mgx. Okay, and the remaining mgx, which is the plus. Now plus sign, plus mgx minus mgx cancelled, so the total energy is mgh. So this is in the second case. So the first case mgh, and the second case also you got the same thing, that is mgh, which is the total mechanical energy. Okay, go for the third one. I say case number 3. So what's the case number 3? So the body is freely falling from A position to C position. Okay, this is our case number 1. You can write it. This is our case number 1. This is our case number 2, and this is the case number 3. So in the third case, the body is moving from A to C directly. The body is moving from or you can say the body is freely falling from A to C. The freely falling from A to C. Okay. So next, so see here, when it reaches the ground, it hits with a particular speed. It hits with a particular velocity. So that is called the final velocity, and this is the initial velocity. Okay. So here the potential energy of a body is taken to be 0, because the body is just touching the ground, means its height is 0, because height equal to 0. Its value is mgh, h is 0, so that's why the total potential energy becomes 0. And what about the kinetic energy? Kinetic energy is equal to 1 by 2 m. It was touching the ground with a particular speed. I call this is a Vc square. What is a Vc? It's a velocity or a speed at the C point. How to get its value? Again the same thing, Vc square. So this initial velocity is final velocity, and it has to cover h distance. It has to cover the h distance to move from A to C. It has to cover h distance. Okay. So then initial velocity is 0. It was 0 here, and plus. So which formula I am using here? V square equal to V square equal to U square plus 2AX. U square plus 2AX. I am using this formula. So, final speed is equal to, initial speed was 0 and 2 as it is, and was acceleration due to gravity and is freely falling, means moving downward, the G is taken to be positive, while upward the G is taken to be negative. Here it is positive. So, and for what distance it has moved? So, to make U equal to 0 to V value, it has covered H distance, alright, H. Is it? So, Vc square equal to 2 into G into H. Okay, and substitute this here. So, therefore, kinetic energy is equal to 1 by 2 m into Vc square. Vc square is 2 into G into H. So, kinetic energy is equal to 2 to cancel, this become mgh. So, in this case the total mechanical energy I write in short form ME. Total mechanical energy is equal to potential energy plus kinetic energy. Here the potential is 0 and the kinetic energy is mgh. Is it? Okay. So, finally, total mechanical energy is equal to m into G into H. Say this is equation number 3. Okay. Observe the equation number 1 mgh. Observe equation number 2 mgh. Observe equation number 3 mgh. It means we have calculated was the total energy at A mgh, while total energy at B mgh, total mechanical energy at C is mgh. Is it? So, this is the proof of conservation of mechanical energy. And see from A to, when the body is moving from one position to another position, or when the position is changed or the case is changed, the potential energy may vary or kinetic energy may vary, but the sum of kinetic and potential will be constant. Suppose the kinetic energy is decreasing, the potential energy will be more. Suppose potential energy is decreasing, the kinetic energy will be more. So that the sum of kinetic and potential is always constant for a given system under the conservative forces. Is it? Okay. Finally, you should write a conclusion. So, the conclusion is from equation 1, 2 and 3. Equation 1, equation 2 and equation 3. It is clear that there is conservation of mechanical energy. I have written in short form mech energy. Okay. So, if you are written this much, definitely you will get the 5 marks. So, 1 mark for statement, and you should prove it in case of a freely falling body. We have to take the 3 cases, A point, B point and C point, get the total mechanical energy, I mean potential energy and kinetic energy separately here and add them. Kinetic energy and potential energy separately here and add them. Kinetic energy and potential energy separately and add them. You will get the same value. So, that indicating the conservation of mechanical energy. The next point is potential energy of the spring. Potential energy of the spring. Okay, see here. So, this is a rigid support. It is a rigid support, and there is a spring. There is a spring of this much length. So, if you apply an external force, so there will be the expansion in the spring. Okay, like this. Is it? Okay. Now, this is the applied force. As a result, they developed a restoring force. For that restoring force, I can also call the spring force. Okay, and this is your applied force, Fa. So, here it is not applied force. Okay, there is a applied force. I write Fa, right? And this is called the displacement X, expansion, or you can say how much the spring is displaced from here to here. Okay, right. So, this is the case, and was a potential energy stored in that spring. How do you say it is storing the energy? So, you remove that force, so it will comes back to its original shape and size. Okay, it means it is having some stored form energy. We have to calculate that energy, and we know the spring force. Spring force is not a constant force. Okay, so it is variable force, but it is conservative. It is variable. It is variable and conserved force. And conserved force. And here, if it is a constant force, directly you can use the formula work done is equal to force into displacement. So that value itself here will be its energy. But here the force is variable one, and how to get the work done in case of variable force? By using the graph. So we now plot the graph of force versus the displacement. And for the spring, we know that a spring force is directly proportional to displacement. Directly proportional to displacement with the negative sign. See here, the displacement is in this direction, displacement is like this, and the spring force is here. It is an internal force, restoring force. Okay, here. So that's why the angle between these two is 180. Okay, so somehow the force and displacement are in opposite direction. That's why this is minus sign. So Fs is equal to minus into k into x. Minus into k into x, where k is spring constant. Okay, I'll draw the graph. So that is, so along the y axis this is the force, along the x axis this is the displacement. If I take the x as a positive value, I should take the F as a negative because of this relation. If I take this as a positive, this must be negative. If this is positive, this must be negative. Okay, so I take the displacement as a positive, so that's why the force is along the negative y axis. So, and force, this is F and this is displacement. So F and displacement, they are directly related. Directly related means the graph is like this. As you increase the distance, the force increases, and finally you will get a graph like this. Okay, so this will be the graph of force versus displacement in case of spring force. And I want to get the area under the curve. Okay, take this much of this one. Okay, this become the displacement and this become the force. This is spring force. Okay, this is force, right? So I can write it. So work done is equal to area under curve. Area under that curve. This curve the area, right? So I can write it as 1/2 base into height. 1/2 base into height. Okay, so work done is a scalar quantity, no need to take the positive or negative. Here the base is, so this is the base or this is the base. Illi ನೀವು ಕನ್ಸಿಡರ್ ಮಾಡಿದ್ರೆ ಈ ಟ್ರಯಾಂಗಲ್ ಇದು ಬೇಸ್ ಆಗ್ತದ ಇಲ್ಲ ಇದು ಬೇಸ್ ಆಗ್ತದ. Is it? Okay, how much the base is? It is x. Okay, into how much the height is? This is the spring force Fs. Okay, so then 1/2 force into displacement. Force into displacement, that will give the work done. Is it? Okay, so F into x. So x as it is, the Fs as it is. Substitute the value of Fs. Was the value for Fs? So 1/2. This is into x into Fs. Okay, 1/2 x as it is, and Fs is minus k into x. So finally this become work done is equal to minus half k into x square. Minus half k into x square. Is it? Okay, so for this work done is stored. This work done is stored in the spring as the potential energy. This work done is stored in the spring as a potential energy. So that's why I can write the potential energy of a spring is equal to work done in that case. So that is minus 1/2 k into x square. Minus 1/2 k into x square, where k is a force constant or spring constant and x is the displacement. Okay, so potential energy is equal to minus 1/2 k x square. Okay, next point is about the power. So how do you define the power? Okay, see here you may use the word power in many cases, but I love power already. Here it is about the mechanical power. Okay, how to define the power? So it is the rate of work done or the rate of energy, the time rate of work done or time rate of energy. So that is called the work done. For example, we are using the electric energy to burn the bulb or to rotate the fan. Electric energy ನಾವು ಫ್ಯಾನ್ ರೊಟೇಟ್ ಮಾಡಲಿಕ್ಕೆ ಅಥವಾ ಬಲ್ಬ್ ಆನ್ ಆಗಲಿಕ್ಕೆ ಯೂಸ್ ಮಾಡಲಾಗ್ತದೆ ಅಂತ ತಿಳ್ಕೊಂಡ್ರಿ. ಸೊ ಎನರ್ಜಿ ಸಪ್ಲೈ ಆಗ್ತಾ ಎನರ್ಜಿ ಸಪ್ಲೈ ಆಗ್ತಾ ಇರ್ತದೆ. ಒಂದು ಸೆಕೆಂಡಿಗೆ ಎಷ್ಟು ಎನರ್ಜಿ ಕನ್ಸ್ಯೂಮ್ ಆಯಿತು, ಒಂದು ಸೆಕೆಂಡ್ಗೆ ಎಷ್ಟು ಎನರ್ಜಿನ ಅದು ಬಳಸ್ಕೊಂತು. ಸೊ ದ್ಯಾಟ್ ಈಸ್ ಕಾಲ್ಡ್ ದ ಪವರ್. ಸೊ ಪವರ್ ಮೀನ್ಸ್ ದ ಅಮೌಂಟ್ ಆಫ್ ಎನರ್ಜಿ utilized in 1 second, amount of energy supplied in 1 second. Okay, so I can write it as power. P is equal to work done divided by time. So the value of work done is equal to energy. So you can write the rate of work done, the rate at which work is done, that is called the power. Or you can say the rate at which energy is transferred or energy is consumed, so that is called the power. So the power is the rate of work done, the rate of work done. And here we can study the power under the two headlines. So like in average power, and second one is instantaneous power. Instantaneous power, average power or instantaneous power. Average power, how to get the average power? We can get it like a total work done divided by total time for that work done, total time taken, total work done divided by total time taken. Or you can write a total energy transferred divided by total work done, total time taken. Is it right? Or you can write instantaneous power as the limit of average power, the limit of average power as a delta t tends to 0. So I explained this thing in the third topic. So how to take the delta t tends to 0. So we can define like instantaneous power is the limiting value of average power as a delta t tends to 0. Okay, somehow you should remind this equation. So P is equal to W by T, or P is equal to energy by T. So this is the basic formula. Okay, I want to write the SI unit. SI unit of power. So is equal to, for the work done, this is joule, for energy is also joule, and divided by second, joule per second. So joule per second. So this is termed as the watt. So SI unit of power is, you should write with a capital W, or you can write it in words like a watt, WATT. SI unit of power is a watt. Is it clear? Okay, can you write the value of the power in terms of the speed and force, or in terms of the force? Okay, we'll try. So power formula P is equal to work done divided by time. So for the work done, I can write a force vector into displacement vector, divided by time. So take the F separately and the dot operation as it is, and the displacement vector divided by time. Now displacement divided by time is the velocity, so this become velocity. So we can write P is equal to dot product of force and velocity. So force is a vector quantity, velocity vector quantity. Under the dot operation, they results a scalar. Is it? So that's why power is a scalar quantity. Then how to write the dimension formula? For the work done, you know the dimension formula, that is m L square t to the power minus 2, and there is a one more t here. Now, okay, so force value first m L t to the minus 2, and the displacement, this become work done. Okay, finally this is m L square t to the power minus 3. m L square t to the power minus 3 is the dimension formula for the power. And the SI unit is watt, and its formula is work by time, or energy divided by time. We can also write it as force into velocity. Okay, so you may heard one more unit, that is kilowatt hour. So if you see the bill of the electricity bill, so you may have seen the unit of the energy used, unit of electric energy used is kilowatt hour. So the term is watt here, but still I say this unit, this is not a unit of power. Kilowatt hour is not a unit of power. So it is a unit of energy. It is a unit of energy, or you can say it is a commercial unit of electric energy. Kilowatt hour is a commercial unit of electric energy. Okay, how do you say it's a unit of energy even though it is having the term watt? Watt ಅನ್ನೋ ಟರ್ಮ್ ಇದ್ರೂ ಕೂಡ ಅದಕ್ಕೆ ನೀವು ಯಾಕೆ ಎನರ್ಜಿ ಅನ್ಲಾತೀರಾ? ಬಿಕಾಸ್ ವ್ಯಾಟ್ ಈಸ್ ಈಕ್ವಲ್ ಟು energy joule divided by second. Okay, so I can next watt into second is equal to joule. Watt into second into joule. Okay, so instead of second I can write the term hour also. So watt multiplied by the time that will give the energy. So this is power is equal to energy divided by time. So power into time is equal to energy. So this is a kilowatt. Kilo means 10 to the power 3. Okay, so 10 to the power 3 watt into time. Okay, power into time will give the energy. So SI unit of power into SI unit of time will give the SI unit of energy. Okay, so this becomes joule. So kilowatt hour is a commercial unit of electric energy. So ಅಲ್ಲಿ ವ್ಯಾಟ್ ಅನ್ನೋ ಟರ್ಮ್ ಇದ್ದ ತಕ್ಷಣ ಕನ್ಫ್ಯೂಸ್ ಆಗಿಬಿಟ್ಟು ಇಟ್ ಇಸ್ ಅ ಯೂನಿಟ್ ಆಫ್ ಪವರ್ ಅಂತ ಅಂದ್ಕೊಳ್ಳಿಕ್ಕೆ ಹೋಗಬೇಡ್ರಿ. ಓಕೆ, ಸೊ ದಿಸ್ ಇಸ್ ಅಬೌಟ್ ದಿಸ್ ಕ್ಲಾಸ್.